All right, so we are going to look at random number generation with Numpy. All right, and as usual, we need to start off by importing. Let's make sure I've got everything restarted and cleared. Good. So we need to import Numpy, and I'm going to do that as MP. And also for this video, even though you might not be familiar with this library, I am going to import matplotlib.pyplot as PLT. All right, so this is a very basic plotting utility available in Python, used a lot for scientific computing, and there will be a playlist up going over the basics of matplotlib. Today, I'm just going to use it to make some very simple visualizations. Nothing too difficult. So even if you haven't watched that playlist or seen dealt with matplotlib in the past, it should be relatively straightforward. Of course, you will need to have matplotlib installed. So if you're like me using Anaconda environment, you will need to have done a conda install matplotlib, either from just regular conda install or using the CondaForge channel. And if you're using just regular Python, you'll need to do a pip install matplotlib. All right, so up to this point, really, we've just been looking at this NumPy array object and creating arrays with lists. But another thing that you can do is you can generate arrays randomly. And this is, of course, not the only way. There's a lot of other utilities built into NumPy to allow you to generate arrays of, say, zeros or ones or whatnot of a particular shape. But what we're going to be doing is looking at NumPy's random value generation capabilities. So to do this, NumPy actually has a module called random. All right, so if you do a num_mp.random, and then if I do a dot and tab or a period and tab, you can see that I've got access to this, another set of methods, attributes, and these are related to random number generation. All right, so the first thing that I'm going to do, we're going to start really simple. There is a function called rand. All right, now if I hit this, right, so I'm just shift enter, you can see that what I'm getting is random floating point numbers, or seemingly random floating point numbers. Let's actually get inside our parentheses, hold down shift and hit tab, right? And then, it just says, hey, I'm going to give you random values in a particular shape. And what it's doing is it's essentially drawing random samples from a uniform distribution, including 0 and going up to, but not including 1. All right, so this just generates random floats in between 0 and 1. All right, the one thing about this that you'll note is every time I am executing this cell, I'm getting a different number. Right? You might say, well, that's expected because you're generating random numbers, but sometimes you don't want truly random numbers. So imagine that you're writing some type of an algorithm that depends on there being some type of a random element, and you want to compare different versions of that algorithm over time. Maybe there's some type of a performance metric that you can use to see the quality. And what you would like to do is make sure that when you do those comparisons over time with maybe different configurations, different settings, that it's an apples to apples comparison. Well, if you can never guarantee that the numbers you're getting back from this random number generation are the same, it's hard to compare the performance of, say, configuration A to configuration B because, maybe they use different random numbers under the hood. So maybe you want a way of saying, okay, well, I want seemingly random numbers, but I want to have the same random numbers for different replications or different configurations of this algorithm or procedure that I'm testing. All right, so you can do that because actually the random number generator that NumPy is using, and this is actually true of pretty much every programming language that has number generation, random number generation capabilities, they're pseudo-random. So there's an algorithm that is generating those random numbers. They're not true random numbers. They're not cryptographically secure random numbers, but they are generated from an algorithm to essentially mimic a random situation. All right, and the output of that random number generation scheme or algorithm is going to be dependent on a seed value. And that seed value could be set from, system parameters of your machine, maybe your operating system, maybe the system time. It uses, those parameters, either your operating system parameters or the time, as some type of an input to dictate what numbers it's giving you. So you're essentially seeding the random number generation with some of those parameters. All right. Well, you can actually, specify a seed. So the first thing that we're going to look at is, how do we specify a seed? And you're going to see me do this a lot throughout this video. Well, if I go np.random, that module, there is a seed function. And you can provide an integer value, right? So you provided a seed, and it's going to reseed the random state. So watch what happens now. Every time I run this, I'm getting the same number. All right, so this is called seeding your random number generation. All right, and it makes sure that if you're doing like a comparison, across, different configurations, well, you can make sure that you're generating the same random numbers, as long as, you initialize to a common seed before you start that random number generation process. All right, so when we're just calling np_rand or np_random.rand, it's just generating one number. But if I show Shift Tab, with this rand function, you can actually provide arguments, and what these will do is give you random numbers of a particular shape. All right, so what would that look like? All right, let's say that I wanted to generate a NumPy array of random numbers between 0 and 1, and I wanted to have, 3 positions in axis 0 and 5 in axis 1. So we could say, give me back a 3 by 5, right? And now we've got essentially a NumPy array of random floating point values between 0 and 1. And because we're using that seed, right, everything, it's always the same. Now, if I make this call again down below, now it's changing, right? So the thing is, that seed is right there. Every time I'm executing this cell, I'm first initializing the seed to 0, then I generate my random numbers. So just to show you a few different configurations of that, right? So watch this. So if I set my seed and then I generate those numbers once, it's going to match, right? It's the same as calling the seed and then setting the random in the same cell. But now every time I generate those random numbers again, I'm getting different ones. Right? It's because, again, the first time that we generated, it was starting from that seed of 0, and then it's just continuing on in that algorithm. So to guarantee that, that's why I'm putting them in the same cell. So every time I'm executing it, it's first setting that seed. All right, so that's rand. And one thing that's interesting about the rand function that kind of differs from other ones that we'll see in NumPy, and you can kind of get a hint at this in the documentation. So it says, hey, this is a convenience function for porting code from MATLAB. So basically the way that it's indicating the size, you provide different arguments. So this is how many positions I want in axis 0. This is how many I want in axis 1. And we won't see that syntax in the other function. So this is kind of the one, special case. All right, let's look at some other functions. So I'm just going to do an np.random. I'm going to do this pretty much every cell. All right. We can also, instead of using the rand function, if we wanted to get uniform or values between 0 and 1, we could do an np.random, and then there is a uniform function. All right, you specify the low and the high. Right, it says I'm going to generate from low to high. It excludes the high, so it's essentially the same behavior as high. But now we have a size argument. All right, so by default, low is going to be set to 0. And by default, if we do nothing, high is going to be set to 1. So I'm going to provide this size argument. And I am going to set that equal to 3, 5. So that's how it expects that argument. It needs to be a tuple, right? So in just the tuple is going to be the number of elements you want in each axis. So I want 3 elements in axis 0, 5 in axis 1. And now we generate that, and it gives us essentially the equivalent result, right? So you can see that these two methods are related. Just wanted to show you this one special case if you ever do rand. If you don't want to remember the special case, you can always remember you can just do .uniform and pretty much emulate that behavior. All right. So it's not just generating uniform random numbers. We have a tremendous amount of generators that we can use. Right. So let me do my random seed trick. All right. So we can look in our random library. All right. And we actually have normal. So if you want to generate random values that follow a Gaussian or normal distribution, you can use this function. It takes two arguments, location and scale. And these are going, let's just make sure. So yeah, your location is the center of the distribution. So where you want the center of that normal distribution to be that you're generating values from. And then the scale. So that's going to control the standard deviation, right? So by default, loc is 0, scale is 1, and we can provide again a size. So let's just, in this case, let's just say size is equal to, let's generate 100 of these. All right, so it's generating some normally distributed random values with it, where that normal distribution has a mean of 1 and a standard deviation, or a mean of 0, I should say, and a standard deviation of 1. So I'm just going to store these. Normal RVs. All right. And again, I'm just going to put a little bit of machinery together just so that we can, visualize these. So right now we've got these normal random variables. It's hard for me to tell if that's actually normally distributed. So this is where I'm going to use matplotlib. And again, if you haven't seen matplotlib, so this is going to be just a very simple function. Again, there's going to be a playlist going over the basics of matplotlib. But right now I'm just going to generate a simple visualization. And again, you won't understand this at this point. But what I'm going to do is I'm going to generate essentially a figure that has one row and one column of subplots. I'm going to make it where the width is a little bit greater than the height. And then I am going to call hist on my normal random variables. And then let's just say, let's do 20, let's just do 10 bins maybe. I'm going to make it look trying to make it look somewhat decent. So putting borders on those bins, and then I'll do a plt.show. So all I'm doing is creating a histogram with my normal random variables, just so that we can make sure that this is in fact generating random values that follow or mimic a normal or bell-shaped Gaussian distribution. All right, so this looks decent, right? So we can see that this distribution seems to have the majority of its mass at 0. So a histogram, it's just breaking up the values. So if I were to look at these normal RVs and get them in, right? So the lowest value it sees is negative 2.55, and I get the max. That's 2.26. It just takes the interval between the min and the max, and it breaks it into bins of equal width. And it's just counting the number of observations that fall within each. So for a normal distribution, we would expect the majority to be in that center bin that's corresponding to the mean. And then we've got our standard deviation, which is controlling the spread. All right, so if I generate more, let's generate 10,000 of those random variables, right? All right, now we can start to see a little bit more definition. Let's give this bins just a little bit more. Let me say, let's do 25 bins. All right, so this looks like a good normal distribution. So we're using Numpy and we're able to generate those normal random variables. What I'm actually going to do is I'm going to copy that down, and I'm going to put our function as well, or not our function, but our plotting code right there with this. All right, so again, this is just running everything together. So we set our seed, generate our random values, and then all of this code right here is doing that simple plot. All right, you can also do different distributions. So instead of normal, what if we wanted to do a triangular distribution? So with a triangular, you have to give it a left, so essentially a lowest possible value, a most likely value, and then a highest possible value. All right, so we can provide those three parameters. And in this case, it looks like, those can be positional, parameters, so I can give it the left, the mode, and then the right. So let's just say, triangular, let's say 10. The most likely value is going to be 30, and then it can go as large as 200. Let's generate 10,000 of those. And I'm going to, instead of calling this normal, I'm going to call this triangular RVs. And there's our triangular distribution. So it went as low as 10. It went all the way up to 200. And the most likely value is right in this area around 30, right around what that peak is. All right, so there's a lot of different distributions that you can choose from. And again, this will be repeatable because I'm setting that seed. All right, another capability that I want to show you. So again, you can go through and look. There's a good number of distributions. This is really helpful if you're doing some type of a simulation or you've got some type of an algorithm that depends on randomness. Another thing that I tend to use the random capabilities from Numpy for is maybe taking a random sample of some other object. All right. So to show this, let's just say that I've got a Numpy array. So I'm going to do an NP array, and let's make this one good and easy. All right, and I'm going to say that this is going to be my array. All right, so right now we've got a Numpy array. It includes the integers from 1 to 10. All right. And again, what I want to demonstrate here is how you can randomly sample from a collection using Numpy. So again, I'm going to set my seed because even though we're not generating numbers here, we're essentially generating random index values, and we're going to select the values from those index positions to return. All right, and the function that you will use, so you again go in NP's random module, and it's called random.choice. All right, and what you have to do, you have to provide an array, so that's required. There's no default value there, so you have to provide an array. You have to tell it the size of the thing, or you don't have to tell it, though. That's an optional argument. So you have to tell it A because there's no default value. And you can optionally provide a size, this replace argument, and a probability argument. All right, so let's look at those. Right, so let's kind of break those apart. So first, if I just give it my array, it's going to return a single value from that array. So all it's doing is choosing one of those values. All right, and because again I've got this seed set, it's always going to choose the same value in this cell. But if I were to comment that out, right, you can see that it's choosing different values randomly, right? You can also tell it to choose more than one, right? So you can say, well, I want to do something with a size, maybe give me back 5 random values, all right? Now here's one thing to note. So notice when I'm choosing these 5, I actually get repeated elements. Right, so it chose 6, then it chose 1, then it actually chooses 4 twice, and that's perfectly normal for some type of a random selection. So it may very well choose the same value several times. Right, that can happen with a certain probability, albeit choosing the same one over and over again and or consecutively. The probability of that will be decreasing as the number of times that you choose it consecutively are. But it is likely, or it is possible. All right. What if you don't want this? What if you don't want to get the same one? So I've got 10 elements and I want to choose 5 of them randomly. And maybe this is like me selecting winners, right? So I'm not going to choose the same individual twice, right? So I want to make sure that my selection is without replacement. All right. Well, if we get in that random choice, we can see that we do have a replace argument. Okay, so we can say, okay, well, that's going to be true. By default, it is set to true, or you can set that to false. And when you set that to false, it controls whether or not that sample is drawn with or without replacement. So false means it's without replacement. You're not replacing. All right, so if I set replace equal to false, all right, so now, and let me take this random seed off just to show you. right? Every time it's never going to be drawing the same value. Whereas if we, again, use the default, a lot of times we're getting values that are repeated, right? A surprising amount of times. All right, so that is NumPy random choice. Instead of just, returning, size equal 5, you could actually, let's say that, you've got a set of values and you want to come up with an array that's configured randomly. One way to do that, let's say, instead of saying, well, size is equal to a single, value and returning a vector, if I know I've got 10 values, I can say, well, return something that's got, 5 positions in axis 0, 2 in axis 1, and then let's do replace equals false. All right, so basically what it's done is it's taken those 10 values and it's returned a 5x2 data structure where those values are placed in it randomly, right? So you can do things like that as well. One last thing that, or two last things. So first off, if you were, in this case, if I try to generate something that has, 10 index positions in axis 0 and 2 positions in axis 1, this is going to fail, right? Well, why is that? Well, because replace is equal to false. So I'm not allowing replacement. I've only got 10 items, and I'm telling it to make a data structure that has 20 items. So it's going to say, hey, I can't take a sample larger than the population where our original array is the population when replace is equal to false. So you can run into errors if you're not careful like that. But if we do this with replacement is equal to true, we can see that in fact we do allow that, right? All right, and one last thing that I want to show you is that p parameter. So if you remember when we do np.random.choice, all right, so you've got this p argument. And what you can do is if you've got an array of a fixed size and you know that certain observations should be drawn with a certain probability, you can use this p argument to control that, right? So let's imagine that we only had two values, 0 and 1. All right. So if I do random choice, you can actually provide it like this. Say, well, I don't necessarily have to provide a NumPy array. It will actually work with a list. And now I can randomly choose values from that, right? Well, what if I wanted to say, well, the probability of getting a 0 is much higher than the probability of getting a 1? This is how you can indicate that. So in this case, I'm saying, well, here's your choices. So if I look at my arguments, this array A, right? So it says, hey, that's a 1D array like, right? So that's why the list is working, because this is array like, or it's an integer, right? So in this case, I've provided a list for A. It's got 2 elements. And then for P, I'm providing a list of probabilities. And the dimension of this list matches the dimension of the thing I'm passing in as A. So now we should see that it's much more likely to get zeros than it is to get ones, right? And in fact, let's generate, so I'm going to put in that size argument. Let's generate 100 of those. Right, so you see what it's doing. So it's generating 100 zeros or ones based on that probability, where 0 has a 90% probability, or a 0.9 probability of being drawn, in contrast to the 1 that has a 0.1 probability. All right, so now if I were to say, okay, well, this is going to be my RVs. All right, so this is a NumPy array. So one of the methods I can use is I can get the mean, and the mean is just going to sum up the values and divide it by the number of entries. So this is essentially giving me the proportion of values in that NumPy array that are equal to 1. So we can see that, okay, well, in this case, the proportion is about 0.07. So the way that we drew it, the likelihood of drawing a 1 is actually a little bit less than that 0.1. Okay, so it's not exact. in the sense of you can't guarantee that you're going to draw exactly that many because it's a random number generator under the hood. But what you should see is that as the size of the set of numbers that you generate increases, you should start to converge more towards that true probability. All right, so in this case, we get to 0.097 when we generate 10,000. What happens if we generate a million? Right, we're pretty close, so we're getting closer and closer. So what you'll see is that, again, as you get closer and closer to, or generate a larger number of random values, you're going to get closer and closer to that specified probability. All right, so that is a real quick overview of NumPy's random number generation capabilities.